Methods via automata and bounded tree widths, classical automata theory, deterministic finite automata. Many of the methods we use on graphs are analogs of methods used for languages accepted by finite automata. Because of this, in the next few sections, we will give a self-contained account of the aspects of classical formal language theory which we need. We begin with the finite automata. Definition 6.1 Finite automaton. A deterministic finite automaton is a quintuple m equals to k sigma delta SF, where K is a finite set called the set of states. S, which is a set or subset or equals to K, is called the set of initial states. F, which is a subset or equals to K, is called the set of accepting states. Sigma is the finite underlying set, and delta, which maps from the product of K and sigma to K, is the partial function called the transition function. We will usually denote states by the set Qi such that I in G for some set G and have S equals to the set Q0. As the reader will recall, we think of automata as physical machines that act to accept or reject streams from sigma star. We consider the machine M as starting on the leftmost symbol of a stream rho in sigma star in state Q0. The transition function delta induces a rule if M is in a state Qi reading A, which is in sigma, move one symbol right and change the internal state of M to delta of Qia. For each gamma in sigma star, we may write this action as Qia gamma yields to delta of Qia gamma. Here the symbol is read as yields in one step. We say that M accepts a string row if after starting M on input row in state Q0 and then applying yields in one step in the size of row times, M is in one of the states in F. More formally, one can define M to accept a row if, for some little f in capital F, Q0 row, which yields in one step star to the tuple F lambda, where lambda denotes the empty string and yields in one step star denotes the transition closure of the yield symbol. We let L of M equals to the set row in sigma star such that M accepts row. Example 6.2. Let K equals to the set Q0, Q1, sigma equals to the set 0, 1, S equals to the set Q0, and F equals to the set Q0. We have the state Q, the symbol of A, and the delta Q of A as follows. Q0 with a state Q0, symbol 0, delta Q of A becomes Q0. Q0 with the symbol 1 will move to Q1. Q1 with the symbol 1 will move to Q0. Q1 with the symbol 0 will move to Q1. Now as Q0 in F, M accepts 00110 and hence 00110 is in L of M. On the other hand, one can easily see that Q0 0010 yields star of the tuple Q1 lambda, and since Q1 is not in F, 0010 is not in L of M. The traditional way of representing automata is via transition or state diagrams. Here there is one vertex for each of the states of M and the arrows from one state to another labeled by the possible transitions given by delta. Accepted states are usually represented by a double circle at the node. For instance, the machine M would be represented by the diagram in figure 6.1. In this simple machine, Q0 has a double circle around it since it is an accepted state, whereas Q1 has only a single circle around it since it is not an accept state. The crucial fact we will need in our investigations is that for a fixed M, one can quickly decide if a row is in M. That is, we note the following trivial observation. Deterministic finite automata acceptance. Input a string row in a sigma star. Parameter M, a deterministic finite automata over sigma star. Question, is row in L of M? Observation 6.3 Deterministic finite automata acceptance is big O of the size of a row and hence is strongly uniformly FPT. The point of the story is that finite automata provide a canonical way of demonstrating that a given problem is FPT, although not many graph theoretical problems are accepted by standard automata like those above. We can use the classical theory as a good basis for our approach to modified automata that are more attuned to graph theoretical properties. Before we do so, we will need to develop a bit more of the classical theory. The following exercises should provide the reader unfamiliar with the automata with a little warm up to the next sections.